So again, on these ones, I've written down the formula. We had to find the SP squared by taking N1 minus 1 and the standard deviation sub 1 squared, N2 minus 1, the standard deviation squared. On the bottom is the degree of freedom, which is the N1 plus the N2 minus 2. Once we found that number, we plugged it into our formula in order to find the confidence interval on this one. And so if you're not logged into Alex, you'll need that in order to do our calculations once we get there. So, it says managers of an industrial plant want to determine which of two types of fuel, gas, or electric is more cost efficient measured in cost per unit of energy. Independent random samples were taken of plants using electricity and plants using gas. These samples consisted of 11 plants using electricity, so N1 is going to be 11, which had a mean cost of $50.70. So X bar 1 is going to be my mean cost, $50.80, and a standard deviation of $8.67. So S1 is going to be $8.67. My second one, we are going to do 15 plants using gas. So N2 is going to be 15. Which had a mean of 50, whoops, I put the wrong mean on the first one, didn't I? When you go back and forth, it's sometimes hard to see. My first mean was $50.70 with standard deviation of 867. My second one has a mean of $50.80 with a standard deviation, so S2 is going to be $7.98. Assume that the populations of costs per unit are normally distributed for each type of fuel, and assume that the variances of these populations are equal. Construct a 90% confidence interval for the difference between the mean 1 and the mean 2, and then for the plants using the electricity. Carry your intermediate computations to 3 decimal places. Round your answer to at least 2 decimal places. So, we said, first of all, that if I had a 90% confidence interval, that our 90% was in the middle, right? And that we would have 5% on both ends. By now, I hope you know how I got those. So, here, when we do this, 0.05 is going to be our T sub value there, since we have 5% on both ends, right? So, in the first part of our formula, when we find our SP squared, we are going to do N1 minus 1, so 11 minus 1, times the standard deviation squared, so 8.67 squared, plus N2, so 15 minus 1, times its standard deviation squared, 7.98 squared, and then we're going to divide that by the degree of freedom, which I'm just going to figure out over here. I would take my 11 plus my 15 minus my 2, because I need that when I do my T anyway. That would give me 26 minus 2, which is 24. So I'll just put a 24 down there on the bottom. And you can either use the Alex calculator for that or your regular calculator, since we don't have any of the T stuff. But if you calculate that out, we're going to carry that out to 3 decimal places. Yep, 68.467. So now we're going to use the second part of our formula over there to find the confidence interval there, the lower limit and the upper limit. So X bar, which is the mean of 1, minus X bar 2, which is the mean of 2. So we're going to have 50.70 minus 50.80 plus or minus t sub 0.05 with a degree of freedom of 24, which should be our same number we used under our fraction, right? And then we're going to have the square root of that number we just found, 68.467, 467 if I write the right number down, times 1 over n1, which is 11, plus 1 over n2, which is 15, and that's the formula that I'm going to type in to find my confidence interval. I'm just wondering where you had been. We're on homework 18. We didn't quite get it finished last time because they came in and did a survey. So we got a little behind. Yep, we're rounding to 2 decimal places on our final answer. So our lower limit should be negative 5.72. Our upper limit is going to be 5.52, exactly. So 2 different formulas that you have to do when you do those ones. First, I like to find the SP squared using this formula. Then I can do my confidence interval formula and get my 2 answers. And number 10, 11, and 12, we are again going to do a confidence interval, but this time we're doing the confidence interval for the difference of population proportions. So again, my weird looking formulas. I am going to have p hat 1 minus p hat 2. Instead of doing the mean, I'm doing the proportion that I get in the problem. Plus or minus, this is going to be a z-test instead of a t-test. Z sub, and they're going to call it alpha divided by 2, but we'll figure that out. On the z-test, you don't need the degree of freedoms like you do on the t-test. Then we're going to have the square root of p hat 1 times q hat 1. The q is the 1 minus p over n1 plus p hat 2, q hat 2 over n2. So this is for the difference of my population proportion. An example problem here. It says we have a random sample of 225 bolts from machine A containing 20 defective bolts, while an independent chosen random samples of 200 bolts from machine B contains 16 defective bolts. Let P1 be the proportion of the population of all the bolts from machine A that are defective. P2 be the proportion of the population of all bolts from machine B that are defective. So, P hat 1 is going to be 20 out of 225. I'm going to put the Q down lower because, or not the Q, the P hat 2, my other one. P P hat 2, my other proportion for machine B, would be 16 out of 200. Now, just to check, I didn't do it, I just used the fractions, but do those turn into nice decimals, or are they crappy decimals when you change them to a decimal? If you take 20 divided by 225, does it come out nice, or does it, nope. Okay, then we got to use the fraction. So Q hat 1, we would do 1 minus 20 over 225. The quick way to do that is just take the 225 minus the 20, right? 225 minus 20 would give me 205 out of 225. And for my Q hat for number 2, again I had 16 out of 20 here for P hat, so 1 out of 16 over 200. Why did I say 20? Again, I can just subtract. If I take 200 minus my 16, that will give me my new numerator. 200 minus 16 would give me 184 out of 200. So P hat is my given proportion. Q hat would be the complement, or 1 minus that, so that the two add together and give you 100% of your data. So plugging that into my formula then, we have, switch to blue here, P hat 1, 200, or 20 out of 225, minus P hat 2, which is 16 out of 200, plus or minus, I'm going to go down here, Z sub, now again on this one we have a 90% confidence interval, but the 90% is the part in the middle. And so we want the part on each ends. So again, we're going to use the 5%, and that's why they have alpha divided by 2. There's 10% between each of those, so there's 5% on each end of that to add up to my 100%. So we're going to use Z sub 0.05. Don't have to worry about degree of freedom when you do your Z's. Then we're going to do 20 over 225 times 205 over 225 all over 225 plus 16 over 200 times 184 over 200 all over 200. And that's the crazy looking formula I'm going to punch in on my ALEKS program. We've done already. So you want to punch that in on your calculator all together so you can find your lower limit and your upper limit. By the way, if you're doing a fraction on your keyboard, you can just hit the slash. So if you do 20/225, it'll put that fraction there for you instead of having to click up and down and all over the place. While we're on ALEKS, so we can practice a bunch of these ones in. Do you not have your homework pages with you? We just haven't done them all yet. Okay, let me print this out for you. Well, she's working on that. We'll see if it clears out my whole thing. Oh, it might. When we're done with this one, I'll print it out for you. Otherwise, it'll clear all my writing. When we get that, I'll type in. Make sure, whoops, back that up a little bit. You want to be right behind your fraction, and then you're going to do your times. Whoa, undo. So you have to, there you go. Now times. Yep, because you got to do the 205 over the 225. You have to take the P. Yep, you have to, whoops, oh, you didn't have that in there. You have to have P. Oh, there it is. Oh, yeah, okay, yeah, right there. Those are times. Those are times. P1 times Q1 and P2 times Q2. Those are times. There we go. So then we're going to have 205 over 225. Now we're going to highlight all of that part. Just click, we'll get to that. Oh. Because we have to put all of that over the 225. So divided by 225. Now we're going to go over to the side. And behind that big huge fraction, we're going to put our plus sign. Yep. So it's still under the square root. Whoops, nope, we have to go back a little bit further. Evidently that didn't quite work right there. There we go. Now we're going to do our other fraction. 16 over 200. 200, yep. And right behind that fraction, you're going to do the times. 184 over 200. Then we're going to highlight those two fractions and divide that by 200. There we go. And hit equals. So when you notice right here, that is not under the square root. So if I'm just going to do, you want to make sure, whoops, that was 225, that you click right behind that fraction. So there's no space there. So when you do the times, it stays there. And then we had 205 over 225. And when I highlight, I'm just going to highlight from, whoops, why didn't I want to do that? I don't want that whole thing. I'm going to go from there to there. And then I'm going to divide that by my 225. Again, when I click, I want to click right behind that fraction so that everything stays under the square root. Okay? So, for my lower limit, what did we end up with? Negative 0.03, you got 5?
Yep.
And then for my upper limit?
0.053.
0.053. Wait, just make sure she gets the same answer, just so we know she got those all typed in right. All right. All right, so if you scroll way to the very beginning, did you do the plus or minus in there?
You did plus.
Slide to the beginning of that. Oh, you just did the last part of it. You didn't do the part in the front first set of parentheses that I smushed up there. So add in front of there, parentheses, 220 over 225, then right behind that minus 16 over 200. Close the parenthesis behind that, yep, right behind there. And then the plus or minus in between in front of the z. That's right, yep, there we go. Now let's hit equals. And if we slide to the very beginning, we got 0.0354, right? And then if we slide over to the second answer, 0.53. Okay? So, kind of cumbersome to get typed in, but not really too bad to plug them into the formula. I did mine using a different calculator, so I'm going to fix my answer so that I have the same answer as you guys. Alrighty, number 11 then, same thing. Slide, whoops, I got to put my thing down. Alright, so number 11 again, if I do my formula, I have p hat for 1 minus p hat of 2 plus or minus z sub alpha divided by 2 times the square root of p hat 1 times q hat 1 over n1 plus p hat 2 q hat 2 q hat 2 over n2. There's my formula again if I scribble it up there quick. So on number 11, it says, in a comparative study of 2 new drugs, A and B, 200 patients were treated with drug A, and 225 patients were treated with drug B. The two treatment groups were randomly and independently chosen. It was found that 150 patients were cured using drug A, and 155 patients were cured using drug B. Let P1 be the proportion of population of all patients who are cured using drug A, and P2 be the proportion who are cured using drug B. And again, we're going to do a 90% confidence interval, so we know we've used 90% a lot, that we're going to have 5% on each end when we do our confidence interval. So, P hat 1 would be what proportion? 150 over 200. Just because I'm on number 1, I'm going to also do Q hat 1. What would be my fraction for Q hat 1?
155 over 225.
Whoop, oh, that'd be my 2. I'm going to do my Q with my P.
Oh, the Q? Oh.
Yep.
That would be 50 over 200?
Exactly. 50 out of 200. So those two things add up to 1. Now I'll do my second one. So for P hat 2, my proportion or my fraction would be
155 over 225.
155 over 225. And Q hat 2 would be
70 over 225?
Yep. 70 over 225. Again, the quick way to get those is just take your denominator minus your numerator, and that will give you that number that should be on the top of that second fraction. So, plugging that into our magnificently long formula, we are going to do P hat 1, which is 150 over 200, minus P hat 2, which is our 155 over 225, plus or minus Z sub 0.05, that's our alpha divided by 2, times the square root of P hat 1, which is 150 over 200, times P hat 2, which is our 50 over 200, all divided by our N1, which is our 200, plus P hat 2, which is our 155 over 225, times Q hat 2, which is our 70 over 225, all over N2, which is our 225. Whoop. Negative 0.010.
0.110.
Okay. And my upper limit will be 0.133. Again, due to rounding things, if you're slightly off, it's going to count it correct. When I did it, I was using just the regular calculator and rounding everything off to 3 decimal places. If you use the Alex calculator, it doesn't do any rounding, and so sometimes you get slightly different answers, but it will count it correct either way. All right, number 12. Doing the same thing. It says in a random sample or random independent samples of 225 adults and 375 teenagers, who watched a certain television show. 148 adults and 191 adults indicated they liked the show. Let P1 be the proportion of all adults watching the show who liked it. P2 be the proportion of all teens watching the show who liked it. Find a 90% confidence interval, which we know then we are going to have 0.05 since our 90% is in the middle. So, P hat 1 would be what fraction? Yep, 148 liked it out of the 225. Just going ahead and doing my Q. If P1 is 148 over 225, Q, that's supposed to be a 1. Q hat 1 is going to be
77 over 225.
Yep, 77 over 225. For P hat 2, my proportion for 2 would be
191 over 375.
191 over 375, which means Q hat 2. Definitely don't like to write Q's today.
175 or 176.
We take 375 minus 191.
184.
184. 184 over 375. All right, so now we got to plug those into our formula. And so on our formula, we have P hat 1 minus P hat 2. So 148 over 225 minus 191 over 375 plus or minus Z sub 0.05 times my square root. I'm going to take P hat 1 times Q hat 1. So 148 over 225 times 77 over 225 all over my 225 plus P2 times Q2. So 191 over 375 times 184 over 375 all over 375. You can almost fit that big long formula in there.
.081.
0.081 is my lower limit.
0.216.
0.216 is my upper limit. All right. So not so bad. It's the worst part is getting it typed in correctly once we have our formula there. All right, 13, 14, and 15. We are going to do a confidence interval for the ratio of the population variance. And again, we're going to have some formulas that we're going to use. On this one, you don't have the plus or minus option. You have to do the two formulas separately. So what they look like is this. We are going to do S squared sub 1, which is our standard deviation, over S squared sub 2. Again, that's the standard deviation. Times 1 over, and we're going to do an F test. So we're going to do F alpha divided by 2. That's going to give me my lower limit. To do my upper limit, I'm going to do the formula is going to look pretty close to the same thing. s squared sub 1 over s squared sub 2 times 1 over, and this is going to be f, and I'm going to do 1 minus alpha over 2. So it says, an examination in biology has been taken by biology majors and also by some students from other majors. It is widely believed that the scores for both groups are normally distributed. A random sample of 27 examinations completed by biology majors and an independent random sample of 15 examinations completed by students from other majors are selected. Among the sampled students, the biology major scored a mean of 520.5 points with a variance of 9,781.2. And the students from the other majors scored a mean of 506.4 with a variance of 11,685.6. We're going to do a 90% confidence interval. So again, if we're doing 90% confidence interval, it's 5% here and 5% here. So here, this is going to be 0.05. Here, I would do 1 minus 0.05, which would be 95, right? If I'm at 5% on one end, the other end's going to be 95%. So 0.95 is going to go there. So the s squared 1 is actually going to be your variance, because your variance is your sample deviation squared. So it tells me my variance for my first one was 9,781.2. My s squared sub 2, again, since they gave me the variance in this problem, I have 11,685.6. So if they give me the standard deviation, I have to square it, but since they gave me the variance, it's already squared. And so I just get to plug those numbers into my formula. So for this formula here on the top, I'm going to take my 9,781.2 divided by my 11,685.6 times 1 over, and then I'm using the F option, sub 0.05. Do I have to have degrees of freedom in here? Yes, I do. I figured I did. For my degree of freedom. On my degree of freedom here, let's see, N1, I had 27 in my sample, and 2, I had 15 in my sample. For my degree of freedom, I am going to do N minus 1. So for my degree of freedom in my numerator, I would do 27 minus 1. Which is 26. For my degree of freedom in my denominator, I'm going to have 15 minus 1, which is 14. So number sampled for my first one was 27. Second sample was 15. We minus 1 for each of those. So degree of freedom in my numerator was 26. Degree of freedom in my denominator, 14. I don't even know that I actually need the brackets around that, but they put it there in the formula. You probably don't even need those. That's what you're going to type in to get your first answer, your lower limit. So 9,781.2 divided by 11,685.6 times 1 divided by the F sub, which is over on the right, yep. And we would use 0.05. The degree of freedom in my numerator is 26. In my denominator is 14. And so my lower limit is 0.3,
Are we doing 2?
yes, 2 decimal places.
0.36.
Okay, 0.36. Now, instead of having to retype all of this, if you just hit undo, you can change your 0.05 to your 0.95 in order to do your other problem. Because it's the same problem, we're just going to change it to 0.95. So 9,781.2 divided by 11,685.6 times 1 over f sub 0.95, degree of freedom in my numerator, 26, in my denominator, 14. But if you just hit undo, you can just change the confidence level from 0.05 to 0.95.
1.75.
1.75, exactly what we should get, 1.75. Okay. So, S squared is your standard deviation squared, which is your variance if they happen to give you the variance in the word problem. Number 14 then. Oh, they did give us the squared again. They gave us our S squared. Random samples are drawn independently from 2 normally distributed populations, and the following statistics are obtained. N1 is 11, N2 is 19. We don't really need the mean for our formula, even though they gave it to us. And then our variances, 216.1 and 338.1. So plugging those into our formula, S1 squared is 216.1 divided by S2 squared, 388.1, times 1 over F sub. We are doing a 90% confidence interval. So for our lower one, we're going to use 0.05, right? Our degree of freedom in our numerator, the degree of freedom in numerator is our number for group 1 minus 1. So since we had 11 here, 11 minus 1 would be 10. Our degree of freedom in our denominator, group 2, we had 19. 19 minus 1 would be 18. So there would be our first formula. The second one's going to be the same thing, just changing our 5% to 95%. So 0.23 is our lower limit. .56 should be our upper limit, exactly. All right, one last one on this page. Actuaries use variance parameters when evaluating the cost of life insurance. The variance of the lifespans of population is one of the parameters used for the evaluation. Each year, the actuaries at a particular insurance company randomly sample 25 people who died during the year, with the samples chosen independently from year to year, to see whether the variance of lifespans have changed. The lifespan data from this year and from last year are summarized below. So the current year, the average age was 75.7. Last year it was 75. My variances again, 50.4 and 47.6. And so we're just going to plug those into our formula. Again, they already squared them for us. So we have 50.4 over 47.6 times 1 over, are we doing 90%? Yep, we're doing 90% on all of these. So F sub 0.05. My degree of freedom in my numerator is going to be how many people did they sample? 25. So 25 minus 1 would be 24. And then in my denominator, it's going to be the same thing because they did 25 each year, right? So 25 minus 1, again, it's going to be 24. So they sampled 25 each year, and 1 is going to be 25, and N2 is also going to be 25. So my degree of freedom is N minus 1. All right. And then, of course, you're going to do that for the lower limit, and then the same thing to get my upper limit, only I'm going to use 95% instead of 5%. All that in there.
.53.
0.53 then is my lower limit. And
2.10.
2.10 is my upper limit.